Hello, Riles. For our video summary of lesson 1.7, I really just want to talk about the definition and the idea of continuity again. It's pretty easy to define. You can say that f is continuous, let's say over x equals a, if the limit as x approaches a of f of x is equal to f of a. But this is rarely good enough for assessments because I don't want students just memorizing a simple statement. I'm going to ask them to explain this and illustrate it to demonstrate their understanding. The other issue with this definition is that often students forget about this part and they just hang on to this part, not um, recalling the fact that I suppose we've evaluated dozens and dozens of limits in this course where f of a doesn't exist. And just because f of a exists does not mean that it's equal to the value of the limit. We've seen so many different cases where that's not true. Okay, heck, I can have a function existing at a, but the limit as x approaches a for f not existing is quite common, or at least in our constructions. Maybe not in the functions that we've seen up until this point, but in the constructions that we've done in this course. So make sure that you review this fact that this statement is true only if f is continuous. Let's try writing it in another order, I suppose. Let's say the limit as x approaches a of f of x is going to equal f of a. That's a weird way of writing that. Only if f is continuous over x equals a. This is pretty much, you could say this is what we've been trying to do, I suppose, when we get our expression that we're trying to take the limit of into a determinate form. The determinate form is like a form for which the relationship is continuous over x equals a, or it's an alternative relationship that doesn't have that discontinuity, so that we can use this property to evaluate it. So only if, review that fact. Okay, and then the way that I'd like you to develop an understanding of this statement instead of just memorizing it. There's very few times, in fact, we could probably round it down to 0 times in this course that I'm going to ask you to just memorize a fact. Let's build an understanding here. I generally will ask students to explain and illustrate the 3 conditions required for continuity. And you can sort of illustrate them as well. First off, you need the function to exist. And illustrating continuity, whoops, that wouldn't be f of a, that'd be, let's call it a comma, I don't know, b, and here's f. Illustrate, to illustrate the conditions of continuity, illustrate the problems. It's a lot easier. Like I could show you, look, this function's continuous here, and you're not quite getting what it is that I'm showing. So show me the problems that could occur, the 3 conditions that need to be true for continuity. First off, make sure that the function exists. 1, f of a must exist. You could write this mathematically as f of a must be an element of the real number system. Make sure, again, that you can explain with words as well as interpret symbols. But usually if I ask you to explain things, don't use symbols like epsilon and r. Next condition, the limit has to exist. The behavior from the left has to equal the behavior from the right. Now, this condition right here, you should also be able to explain what must be true for a limit to exist, talking about the left behavior and the right behavior. So you could break this down in a couple of different ways. You could say the limit, the limit as x approaches a of f of x must exist. Okay, I think writing that out in English usually demonstrates a higher level of understanding than someone that just says, lim x arrow a f epsilon r, like that. Fine. Yeah, if you wanted to break this up further, I suppose you could say that I'll do it symbolically. Lim x a superscript plus f x equals L equals lim x approaches a superscript negative f of x. So, in other words, in English, I suppose you would say that the behavior from the left needs to be the same as the behavior from the right. This I'm showing discontinuities because the behavior from the left is not the same as the behavior from the right. Right. And then the third condition here is that these two values need to be true. The value of the function has to equal the value of the limit. And I think the easiest way of demonstrating that not happening is drawing a function where the limit exists and where the function exists, but where the value of the function is different than the value of the limit. So here is, let's call it a comma L, and here is a comma f of a. And notice that in this case, f of a is not equal to L. So in English, I would say the value of the limit as x approaches a must be the same. And if if I haven't mentioned condition 1 and 2, then I might go out of my way to say must be the same real finite number as the value of the function. When x, let's say when x is a. Now, this is, again, pretty easy to write out mathematically. You say the limit as x approaches a of f of x must equal f of a. And I think it's really important to understand that if statement 3 is true, then statement 1 and statement 2 must be true. Like, you can't say that this is equal to something if this doesn't exist. You can't say that this is equal to something if this doesn't exist. Because you can't use symbols like does not exist or infinity here on both sides. They both need to be real numbers, real finite numbers. But as far as explaining to a reader, make sure you walk them through it and show them this has to be true, this has to be true, and they have to equal the same. Sorry, this has to be true, this has to be true, and they have to equal the same value. Okay, I'll go out of my way to prompt you to explain and illustrate the 3 conditions that must be true for a function to be continuous when x is equal to a. And then I suppose if you want to illustrate that sort of truth, because it's usually not a great idea on my communication questions to explain what can't be false instead of focusing on what the question asks you to do. But I mean, like if we illustrated the truthiness of each one of these conditions, it would sort of look like this. F of a must exist. There you go. There's a comma f of a. Cool. The limit has to exist. There you go. And then the value of the function has to equal the value of the limit. I kind of like drawing this one out like that. It's an open dot. You might ask, well, why would you ever do that? I think to really stress the fact that I want the limit to exist, I want the function to exist, and I need the function to exist where the limit exists as well. Okay. To me, though, this looks an awful lot like that. But just drawing this out, I'm not sure illustrates what needs to be true for continuity. Last thing that I want to cover, and I'm pretty sure, I hope we had time to do it in class, is endpoints are another type of discontinuity. We've seen point discontinuities, we've seen vertical asymptote discontinuities, we've seen jump discontinuities, and we were able to use these 3 to sort of illustrate to build the 3 conditions necessary for continuity. But if we check our definitions carefully and fully, then we'll understand that even a function like y equals the square root of x, the limit as x approaches 0 doesn't exist because the behavior from the left doesn't exist. Even though the function exists when x is equal to 0, even though the behavior from the right converges on the output of 0, this function here, let's call it g of x, is not continuous over its entire domain when x is equal to 0. This is where talking about continuity happening over a value might make a little bit more sense. We generally don't talk about it being continuous at a value. We need it to be continuous over a value. And there's no being continuous over 0 here because the function doesn't exist to the left of 0. So it's maybe a more flexible type of language for you to try to use. Okay.